Okay, here, so we've been introduced to the derivative. We know what the definition is. And now we're going to start looking at some techniques for actually computing or finding the derivative. And it's really not practical. What we've been doing, as far as from the standpoint of actually finding the derivative function, is not very practical, because what we've said is this. We said the derivative is the limit of this difference quotient. Now, if any of you ever are asked what the derivative is, you tell them it's the limit of the difference quotient. You don't say it's the rate of change, you say it's the limit of the difference quotient. And what we do is we use the derivative to measure change. But from a mathematical standpoint, it is that. That limit right there is the difference quotient. And what we want to do is we want to see if there's some ways that we can find the derivative without using that definition, because that definition, it's what the derivative is, but when it comes to computing and actually finding, the algebra can get intensive. So let's see if we can figure out some shortcuts. Now, first of all, I want to look at a couple of things. Let's suppose that we have some function here that's really the sum of two other functions. Like, for example, x squared and x cubed. So we have h of x is equal to x squared plus x cubed. In other words, we have a couple of functions here. Now, we've actually done things like this before, but I just want to formally show you a couple of properties that we're going to be talking about. This property here, if we have a sum of functions, notice that if I plug this into the difference quotient, so I would have h of x plus h. Well, h of x plus h is going to be f, not h, but delta x. I forgot we were using that. Delta x, okay? So there's the first part, minus f of x plus g of x, okay? So this is just something that we need to be aware of. So are there any questions? Does everybody see how I got to that point? Okay. So this right here is just h of x plus delta x. This is just h of x. And so we're just straight up plugging into the definition. Now, I can do some regrouping. And if I do some regrouping, notice I can get f of x plus delta x minus f of x plus g of x plus delta x minus g of x all over delta x. Okay? There's what we have. Now, notice that I've got f of x plus delta x minus f of x over delta x and g of x plus delta x minus g of x over delta x. I could split that up if I wanted to. And remember that the limit of a sum is the same as the sum of the limits. So what I could do at this point is break this up. And I could say, well, I'm going to put the f's over here with, just with themselves. And then over here, I've got the limit. I've got this. Now, yes, sir?
Wouldn't that mean that the derivative of h of x is the derivative of f of x plus the derivative?
Yes, sir. Exactly. Exactly. So this right here is f prime of x, and this over here is g prime of x. So the idea here is just to illustrate something. Now, that if you have a function, you can differentiate term by term of that function. In other words, let's suppose that we had something like, let's suppose that we had h of x is equal to x squared plus 3x. If I want to find the derivative, what this tells me is I can just take a derivative term by term. So I could say h prime of x And in our past work, we found that the derivative of x squared is 2x. The derivative of 3x is 3. And we'll talk more about that in a second. But in other words, that right there is our derivative. Now, we could put that into the difference quotient, and we would have x plus delta x squared plus 3 times x plus delta x minus x squared minus 3x. We could use the difference quotient, but what I want to show you is, and that's going to be relevant today, is that you can differentiate across the plus and also the minus. Okay? So what we've learned is this, that if you want the derivative of a sum, okay, f of x plus g of x, if you want this, and it could be plus or minus, that's just going to be f prime of x plus or minus g prime of x. Okay? So that's one of the properties that we've shown here. Yeah, that's always true, provided you do have differentiable functions. And we'll talk later more about differentiability, but we're just getting into this. We want to get rolling with actually differentiating functions. Okay, any questions about that? Now you have to be careful, because if we had a product, if we had f of x times g of x, we can't just say, well, that's f prime times g prime. We can't do that. So only what we can verify, and there's a different technique for finding products. Okay, so, but this is something that we've shown to be true. Now, something else I want to show you. Let's suppose that we want to differentiate a constant times some function. Or we want to differentiate a function and we have a constant in front, like 3x squared or something like that. Well, notice what we can do with that. We could say, well, this is the limit as delta x goes to 0. And let me just put it in up here. C of f plus delta x minus c of f of x. Okay. Could write it that way if I want it. Okay. And notice I can factor out the c. And c does not have a delta x in it. So really, it doesn't care what delta x does. So I could go ahead and, I could write it this way. I could say the limit as delta x goes to 0 of c times the limit as delta x goes to 0 of this thing. Okay, does everybody agree that I'm not doing anything illegal here? I've just got a constant there, and I can factor the constant out. Now, the limit, this limit right here as delta x goes to 0 of c, c doesn't care what delta x does. It's just itself, okay? So this is really c times f prime of x, okay? So what I'm saying is you can factor out a constant. You can differentiate your function, and then your constant is just along for the ride. Okay? So 5 times x squared, the derivative would be 5 times 2x. Okay? So we know that we can factor out constants. Now, something else I want to point out, think about if you had just f of x equals 3x. Remember that when we talk about a derivative, we're talking about the slope of a tangent. If you look at that function right there, it's not hard to find the slope of the tangent, right? Because the slope of the tangent, this is of the form mx plus b, right? And the slope is just the number in front of the x. So the derivative here, and you could do this with the difference quotient, but you can see that would just be 3. So if you just have x to the first power, you know the derivative is just the constant in front of it. So the derivative of x is just 1. The derivative of 2x is 2, and so forth. Okay? So these are just some preliminary things that we need to take note of. Any questions about that? Okay? But just be cautious. The derivative of a quotient is not the derivative of the top over the derivative of the bottom. What we know right now is the derivative of a sum is the same as the sum of the derivatives. Okay? Now, what I want to look at next is the power rule. So, in other words, if we have a function like x cubed, and we want to take the derivative of x cubed, well, now remember, the derivative is just going to be like this. You're going to have the limit. This is always where we go back. We always go back to the definition. Everything is built on the definition. So I want to go back and say, okay, if I've got a power function like this, what would the definition give me? Is there going to be some kind of formula or some kind of way that I can generalize this? Now, if I multiply out this x plus delta x cubed, what you're going to get is you're going to get this. You're going to get x cubed. The coefficients for cubed are 1, 3, 3, 1. So you're going to get x cubed plus 3x squared delta x. So notice that the delta x kicks in here, plus 3x delta x squared, and then plus delta x cubed minus x cubed. Now, I picked a simple one, but this is the difference quotient for, a very small power up there, 3. Now, notice that it doesn't matter what the power was, if it were 4, 5, 27, or 10 billion, this and this these are going to cancel with each other, right? Because you're always subtracting off this first term, in this case of a power function. Okay? Does everybody see that? Okay. Now, notice what else. Every other term in here has a delta x in it. Every one of them. This term over here has a delta x to the second power. This has a delta x to the third power. This one only has a delta x to the first power, which always means that it will divide out with the bottom. So look, what happens is you're going to have this delta x dividing out with the bottom, and what you're going to have is the limit as delta x goes to 0 of 3x squared plus, 3x delta x plus delta x squared. And then you're going to take the limit as delta x goes to 0, and look what you're going to get. You're just going to get a 3x squared. Okay. Does everybody see that? Now realize we start off with x cubed, the derivative. Now look, we got a 3 here and a second there. So it's as though we brought the 3 out front and then reduced that by 1 power, the exponent by 1 power. Okay? Now, here's the thing. Whenever you expand a binomial, what you can think about the binomial expansion theorem. And for example, when we expand, let me just, instead of a delta x, let me just use an x plus y. If I were going to expand that out, what I could do is I could say, okay, I'm going to have 3 things taken 0 at a time. And this is going to be x to the third. So these combinations generate the coefficients. And then the next one would be 3 things taken 1 at a time. And I would have x squared and then y. And 3 things taken 2 at a time, x, y squared. And then finally, 3 things taken 3 at a time, y cubed, like that. Okay. Now, here's the thing. I don't want to go into it very much, but you can see that the first term is going to cancel when we, like on the derivative, when we were using the difference quotient, that first term is going to cancel. So what we're curious about, and we also know this, we also know that the second term, always the second term in our expansion is going to be 1 power less than we began with, right? So if we had an x cubed, the next term would have an x squared in it. The next term an x, and so forth. If we start off with x to the fifth, the next term would be x to the fourth, right? So you can see that always in our little expansion here, this term is what's going to matter. The y is the delta x, and this is always going to be 1 less. So it looks like when we differentiate, we're going to have a situation with x raised to 1 power less than we started with. Now the question is, well, what is this right here going to be? What is this next term going to be? Well, in the case of this, remember it's 3 factorial over 3 minus 1 factorial times 1 factorial. And notice how this is going to be. This is going to be 3 times 2 factorial over, well, 2 factorial, and those divide out. Now, it's always going to be this way. It's always going to work out this way, where this number right here is the power that we started with. And I'll just leave it for you to play around with that. In other words, we could say this. We could say, well, let's look at combination of n things taken, you could play around with it. Instead of 3, 0, you could have, you could do a fourth degree and so forth, and you could expand that out. And you can easily convince yourself that that number right there is always going to be the power that you started with. See? Let's suppose you start off with a 5th power. Just for example, we would have 5 things taken one at a time. Let's look at how this is going to work. Now notice this 1 here. I have 5 factorial over 5 minus 1 factorial, 1 factorial. Look at this, 5 minus 1, right? So we would have 5 factorial over 4 factorial. Yeah, that's 5. Y'all see that? Because every time you're dividing by the number minus 1 factorial. Any questions about that? Okay, so what we have is this situation. If we're differentiating a power function, let's say x to the n, that's going to be nx to the n minus 1, where n is a natural number. Now, I think you're probably convinced of that. I mean, because you can see, yeah, the second term is going to be 1 less than the first in the power, and also the coefficient is just going to be the power that you started with. I mean, you can see that very easily. So this is what we say, okay, now we're ready to differentiate a power function. We could say x to the 17th power. That would be a real ugly one to expand out, but it's just 17x to the 16th. There it is. And there's our derivative for that one. Yes, ma'am. Exactly. That's a good question. So look, if we have this 2x to the 17th, what we noticed earlier is that you can factor out that constant. You can do this. You can say, well, that's the same as 2 times the derivative, which would be 2 times 17x to the 16th. You can do that. Now, we were kind of formal there, right? I said, well, I'm factoring out the constant. You don't have to do it that way. You could say, well, let's suppose I want to differentiate 8x cubed. Well, that would be 3 times 8 is 24x squared. But what you do is you just take that exponent and multiply it times whatever's in front. Typically, there's a 1 in front. Now, what we've done here is we've kind of shown, I think fairly convincingly, that if you just have a power function, you can differentiate it using this method. And we can put terms together. We could say, well, let's say x to the 4th plus 3x squared plus 5. Something like that. I could differentiate that one. So this would be 4x cubed plus 6x. What's the derivative of 5? You get 0, right? Because 5 is a constant. We've not really talked about that formally, although we did when we talked about graph. But if I ask you, what is the slope of the tangent line, y equals 5? Well, it's a horizontal line. There is no slope there. I mean, the slope is 0. Okay? So there it is. There's your derivative. So we differentiate it term by term. Now here's the thing. We've looked at this for natural numbers. You know, n is 1, 2, 3, 4, and so forth. But actually, and we're not at really this position here that we want to explore this, but it doesn't matter if n is a natural number. Let's suppose that n is just some real number. Okay? If n is a real number, then the derivative is going to be, we can apply the same rules like that. Okay? So I'm using alpha because n is usually reserved for natural numbers. But let's suppose alpha is pi. Okay? If alpha is pi, x to the pi, it would just be pi x to the pi minus 1. There it is, because pi is a number. Okay? Any questions about that? So what we're doing right now, we're being kind of a little bit presumptuous, saying, well, it's working for the natural numbers. Let's just say it works in general. And the reason for that is because we haven't got to the place where we can really show it convincingly that it does work for all these other numbers. But we'll just assume it's true for now, just so that we can get some practice with some more interesting types of problems. Let's suppose I want the derivative of the square root of x. Well, if we can write it this way, x to the 1/2, we're on our way. Because now I can say, okay, that's 1/2 x to the 1/2 minus 1. 1/2 minus 2/2, okay, negative 1/2. And there's my derivative, which I could write that as 1 over 2 square roots of x. Because remember, the negative exponent means wherever it is, it needs to go in the other place. If it's in the bottom, it can go up top. If it's in the top, it can go in the bottom. Now, you could also have 1 over x. Let's see what that looks like. Remember, we write it in where we can see the exponent clearly. Okay, so now we've got negative 1 times x, negative 1 minus 1. That's negative 1x to the negative 2, or negative 1 over x squared. Okay, any questions? Now, there's a lot of problems there's a lot of derivatives, a lot of functions that we can differentiate just with this. And some of them don't look like it at first. For example, maybe we have a function that looks like this. X cubed plus 3x plus 4 over, let's say, x. Something like that. So here's a function at first. We've got this thing on top. We've got something on the bottom. What we can do is we can break this up. And I can call it x cubed over x plus 3x over x plus 4 over x. I can break it up that way. Then, so here's what we have. We have f of x equals x squared plus 3 plus 4x to the negative 1. And that is one I can differentiate with the power rule. Okay, so here we go. F prime is 2x, at 3, the derivative, that's just 0, minus 4x to the negative 2. Huh? Yeah, because but I differentiated it. Yeah, I already ran it through there. Okay, does everybody see that? So this is what we try to do. We try to just get it in a position where we can use the power rule. Now there's something else. You might encounter a function like this. Let's suppose that we've got 2x plus 3 squared. Now, what you're going to do is at this point, you're just going to expand that out. So if we expand that out, and you want to watch yourself and don't just call that 4x squared plus 9, you multiply it out. So you get 4x squared plus 12x plus 9. See? A common mistake is people would just square the first term and square to the second, but that's naughty. You don't want to stay away from that and people that do that. Don't hang out with those people. So now we want to differentiate, right? So this is going to be 8x plus 12. Okay, how does that grab you? Everybody see how this works? Okay, so this is the power rule. And we're just assuming, and so every problem that we work, we try to get to where we can use that x to the alpha, the derivative is alpha, x to the alpha minus 1.